So welcome back to the third day of our workshop, both virtual and hybrid. It's my pleasure to introduce our first speaker for the morning, Will Johnson from Fudan University, who will speak on non-compact p-adic definable groups.
Okay. Oh. Okay. All right. Thanks. Thanks to the organizers for the invitation to speak here. Before I start, in case anybody just joined in the last 20 seconds, let me mention that there's a model theory and there's a conference that I'm helping organize in Shanghai, August 21st to 24th on model theory and on philosophy and mathematics. The website for it is still kind of under construction, but I'm going to put a link to the website in the chat on Zoom right now. And hopefully soon we will put in actual instruction, like a schedule and instructions for registering if people are interested. All right, I think I'll get started then. Okay, so I'm going to be talking today about a project that's joint work with Ningyuan Yao, also at Fudan University. Yeah, we're looking at definable groups in p-adically closed fields. Okay, so like our main result is it's a sort of p-adic analog of a theorem by Peterzil-Steinhorn, I think, about groups definable in O-minimal structures. So I first want to briefly review that theorem. So let's work in an O-minimal expansion of real closed fields. So like an isominimal structure with definable Skolem functions, all those things. And G will be a definable group. It could be an interpretable group. You have elimination of imaginaries, it doesn't matter. And we're going to assume that G is not definably compact. So I'll say more about what that exactly means later. But for now, I want to point out that definable groups in these O-minimal structures they are naturally definable manifolds in a certain sense. Like, well, there's a notion of a definable topological space, a definable set, and there's a topology on it, and there's a basis of opens that's given by a definable family. So that's a definable topological space. And then a definable manifold is a definable topological space where you can cover it with finitely many open sets that are definably homeomorphic to open subsets of m to the n or whatever. And so I think it was Anand Pillay or somebody, maybe not us. I think Anand, who showed that in an O-minimal structure, every definable group naturally has the structure of a definable manifold in a canonical way. So the theorem of Peterzil-Steinhorn says that if you have a group G, so there's a notion of definable compactness in a definable manifold, and I'll say more about that later. If you have a group that is not definably compact, and that group is G, then there is always a one-dimensional definable subgroup H that's not definably compact either. So you can find one-dimensional subgroups that are not compact. You can also make this group H be abelian and torsion-free, I think. So this is a theorem. It's useful for analyzing the structure of definable groups in O-minimal structures. And the theorem, the paper by Peterzil and Steinhorn, they use this to, I think, to analyze the division algebras that are, or division skew fields that are definable in O-minimal structures, maybe. I might have that wrong, but I think that's the actual application. So this is a theorem, and we're sort of interested in generalizing this or finding an analog of this over the p-adic numbers. So this was this original paper by Peterzil and Steinhorn, and there was a later paper, I think, by Peterzil and Starchenko that that gives a more refined view of what's going on, using these notions of mu types and mu stabilizers. So well, so we say that two complete types P and Q that live in this group, two complete types over the model are infinitesimally close if there are realizations A and B, such that A times B inverse is infinitesimal over M. So A times B inverse is an element of an elementary extension, and it is in every M definable neighborhood of the identity. Like it's very close to the identity element of the group. So I think the precise order here means that maybe A and B are connected by multiplication on the left by an infinitesimal, something like that. Anyways, so that's what it means for two types to be infinitesimally close. And then a mu type is an equivalence class of types being modulo being infinitesimally close. There's an action of the m points of G on mu types over M, an action on the left. This feels weird because the mu types are sort of like you're working modulo infinitesimals. Infinitesimals are also acting on the left, but the infinitesimals kind of are preserved under conjugation by elements of M or something. So everything somehow works out. And then you can talk about the mu stabilizer of a type. It's the stabilizer under this group action of the type P's, like the mu type associated to P. So these mu types are somehow like a complete type is like single point in type space, and these mu types are blurred versions of those that move are close by you can like perturb it by an infinitesimal without changing it. And then these mu stabilizers are the stabilizers of those mu types. So I think Peterzil and Starchenko showed that, well, if you have a definable, this is still in an O minimal setting, though later on we'll use these same notions in a other more general settings or different settings. But anyways, this is in the O minimal setting. If you have a definable type, then its mu stabilizer is also a definable group. And that's not the important thing that they proved. But it's true that the mu stabilizer is a definable group. And so the sort of more refined version of the original Peterzil-Steinhorn theorem that shows what's like, this is implicit in their original paper. So if you have a non-compact definable group, you can take a curve that tends to infinity, or basically you take a curve that doesn't have a limit. This is sort of how you can define definable compactness. Let that curve be C. Let P be the type at infinity on the curve. And then the way you get this one-dimensional non-compact subgroup is by taking this mu stabilizer of that type at infinity. I think in this talk, I'm gonna repeatedly say non-compact when I really mean not definably compact. So apologies for that. All right, so yeah, the original paper by Peterzil and Steinhorn basically used this construction to produce this one-dimensional group. And the sort of ideas implicit in that were spelled out later in the paper by Peterzil and Starchenko, who analyzed for a general definable type P in an O minimal group, definable group, what does the stabilizer look like? So they figured out like what the dimension is and that kind of thing.
Will?
Yes?
In general, it's not abelian, the stabilizer.
Let's see. I don't think the stabilizer is in general, I don't think the stabilizer is abelian. I mostly know about the one-dimensional case.
It is solvable.
I'm saying if you
It is solvable. Will.
Oh, it's solvable. Okay.
I mean, I see abelian is missing. So what is it in general not abelian?
Somebody said, I mean,
It is solvable torsion free.
great. It's solvable torsion free. Good.
Okay.
Okay, so there's a question of what does it mean for the curve to tend to infinity?
So what I mean is, okay, so in this case, oh yeah, so the curve tending to infinity. I mean that the curve doesn't have a limit. I mean that the curve is not in a definably compact set, which is equivalent to the curve not having a limit. So like if you have a definable manifold in an O minimal structure, there's yeah, it really just means that like the curve doesn't have a limit. Yeah, it's like going towards one of the ends of so if you think of in like topology, like the ends of a manifold are sort of going towards infinity. It's like going towards one of the ends, basically. It's not contained in any definably compact set. Like that does really mean that you're going towards infinity, because in a definable manifold, you can kind of cover it by an increasing family of definably compact sets that cover the whole space. So the only way that the curve doesn't have a limit is if it goes always towards the edge of those definable compact sets. I mean, definably compact sets. Okay, more questions. Or, oh, wait, let's see. Did I write bounded somewhere? Or
I think that was a
else wrote
reference to something else in the chat. I
Okay.
think we're okay with the chat.
So I am going to use bounded as well to refer to something. And for me, bounded means that a set is contained as a subset of a definably compact set. Which in like if you're looking at something like m to the n, if m is your model, when you're looking at m to the n, then the being bounded in that sense is the same as being bounded in like a more normal sense.
But can you assume your groups are actually subsets of affine space?
Wait, this is talking about the O minimal case right now. I mean, so probably, but in our later setting of p-adics, I think I know. Okay, so the original, like sort of when I joined the project, Ningwen was planning to do this for these affine, or what he was calling affine groups, which were groups that were kind of actually nicely embedded into affine space. I feel that I remember thinking that like you could take any group and do that actually. I mean, over the p-adics, things are very disconnected. It's easy to break into pieces and just stick them in affine space somewhere, but then maybe you get like you don't get a closed set. I don't know. Wait, what was your question actually? You were asking if we can assume
No,
that
I mean that often you could assume that for groups, if you work in the Nash category, then to be affine is a very strong property. But if you work in just a definable, in some smoother category, it's a weaker category, maybe. I forget what happens. Can you assume your groups are affine in some? Never mind, doesn't matter. It's affine. So
oh yeah,
down,
okay. I don't remember what. Yeah, I don't remember what happens. I think maybe, but and over the p-adics, it's a bit easier because of how everything is disconnected. But I think there might be something that goes wrong. I don't remember. Yeah, but if you're like if your group is a closed subset or like a closed submanifold of m to the n, then going to infinity in this sense is the same as kind of going to infinity in a more normal sense. The coordinates blow up or whatever. But yeah, really, you can just assume that this tending to infinity thing means that the curve doesn't have a limit. Oops. Okay. If there's no other questions, I will move on. Okay, so the sort of intuition behind these mysterious mu stabilizers is that at least in the case where you have a one-dimensional type, like the type that's at the limit of some curve going off to infinity, in that case, you should think of these mu stabilizers as somehow being the tangent line at infinity. This was sort of the intuition in the original paper of Peterzil-Steinhorn, I think. Okay, so suppose for simplicity that we have an abelian group. Suppose we've got this curve C that's tending to infinity, and P is our type at the end of the curve. So by the way, everything so far, this whole first section is just reviewing stuff this is not like work that Ningren and I did, but I want to kind of discuss the proof of the things, because our main task was to sort of find an appropriate version of that proof over the p-adics. Okay, anyway, so we have this curve going to infinity in the group, and P is the type at the end of the group. P is this type that's not in any definably compact set. So what does it mean to be an element of this mu stabilizer? So if you have an element T, when is T in the mu stabilizer? If you unwind all the definitions, what it means is that sort of for really far away points X on the curve, X plus T is close to the curve as well. Like really, it's like very close to the curve. Like infinitesimally close to the curve or something. Because what this is saying is that if you take a realization of the type P and then you add T, it's still close to that curve. So rearranging this, what it means to be in the mu stabilizer is that if you take a point on the curve C, if you take a point X that's really far away, and you take the translate C minus X, like you sort of take this curve and slide it back towards the origin, then T will be close to that translate of the curve. And so I'll have a picture of this on the next slide. But the idea then is that this mu stabilizer is like the limit of this translate c minus x as x goes to infinity along the curve. So here's a picture that will help hopefully give some intuition. So here I've got this curve, it's a parabola. Maybe in this case, we're working in like the additive group times the additive group or something. And we're going to take a point on the curve and send it off to infinity, up and to the right along the parabola. And we will take the curve and sort of take that point and drag it back to the middle of this box here. And so we're kind of moving, we're just like moving a window along the curve. And as you move from left to right in this sequence of pictures, the thing inside the window looks more and more like a straight line. It looks like it's the tangent line to the parabola. Somehow the mu stabilizer is the limiting what this curve tends to in the limit. That's the sense in which it's a tangent line at infinity. Right, so that's sort of the idea of the original Peterzil-Steinhorn proof of this fact, that you take a curve, your group is not definably compact, so you can find a curve that goes off to infinity, and you sort of maybe take a sort of window that slides along the curve and like use this sort of construction to find this tangent line, and that in the limit, it turns into like a group. It's not just a curve, it's like an actual subgroup of G, and it's a one-dimensional thing. So that's sort of, if you work through all the definitions, that's what this mu stabilizer actually is. But we still want to prove, I mean, they still need to prove some things about the mu stabilizer. So it's one thing to have the intuition for it, but then we still want to know that it's like a one-dimensional group with various properties, like not being definably compact and stuff. So here's sort of the outline of like a really high-level sketch of the proof. You take this curve C in the type of infinity. So the easy kind of thing is that this is it's a definable subgroup of G, and it has dimension at most 1. Is sort of easy-ish. I mean, it's if you think of it as a stabilizer, it's going to be a group. If you think of it as the limit of this curve, it's going to be one-dimensional because the curve is one-dimensional, roughly speaking. It's less clear. Well, I mean, maybe not that hard, but it's true, and for our purposes, this is like the hard step to show that this thing is not definably compact. And then, which implies that it's not trivial. It's actually got dimension 1. It's infinite. And then also, I guess, showing it's abelian and torsion-free. I don't know if that's easy, but this part, we're not really going to have it. Like, we don't care about this part as much for our work. Was there a question?
No.
Okay, so this part that I've labeled as being hard, how do you show that this sort of tangent line in infinity isn't compact? I mean, it's not definably compact. So the kind of way, here's the way I think about this argument. You fix some annulus A in around 0. Or 0 is, again, I'm using additive notation. 0 is the identity element. And you suppose that, I'm going to be vague about what I mean by an annulus. Suppose that X is a point along the curve and it's really far out. It's like it's close to a realization of this type. So it's close to infinity. And then we form this picture where we take the curve and translate it to move X back to 0. And now this translated curve, it goes from 0 to, it goes from X minus X, which is 0, to infinity minus X, which is still infinity. I mean, in a sense. So the point is that it has to go from 0 to the edge, to the end of the group. And in doing so, it has to cross this annulus. And since like it's an O-minimal, we're in an O-minimal setting, like we can basically assume the curve is connected. And because of that, the curve has to cross through this annulus. So the point is then like somehow in the limit, if we go back to this sort of movie of a window sliding along the curve, that the movie in the limit, it will intersect the annulus in the limit. Like as X approaches infinity, this translates C minus X has to hit this annulus A. So as X goes to infinity, that intersection, which is non-empty, it converges to the intersection of this mu stabilizer with A, this tangent line thing with A. And so that's not empty. I mean, I'm being really vague about like, what do I mean by a set converging to another set? And why does it being non-empty imply that the thing is non-empty? But this is just a sort of intuitive sketch of the argument. And then since A was kind of an arbitrary annulus, like we could have made it as big as we want, it follows that this arbitrarily big sets intersect the mu stabilizer, so that the mu, or more importantly, I guess, the inside of the annulus we can make as big as we want. Like, because it continues to intersect this mu stabilizer, the mu stabilizer has to be non-compact. So one thing to note about this argument is that the fact that things are really connected plays an important role. Like, it's the fact that the curve is connected, we use that to see that the curve can't get from inside to outside without crossing through this gray region in the picture. And that somehow is, no matter how you understand the argument, this is, it plays an important role. So we're going to try to find the analog of the whole thing over the p-adic numbers, and that's where things are going to go really wrong. Okay, so the sort of setting that Nguyen and I are working in, we've got a p-adically closed field. In other words, like a field that's elementarily equivalent to the p-adic numbers. Ideally, we could say some more general things, like about p-minimal structures, I guess, but we haven't really looked into that yet. Okay, we've got a definable group. We don't have elimination of imaginaries anymore. You have plenty of interpretable groups that are not definable, like the value group in the residue field and stuff. So we have an actual definable group, and it's not definably compact. And I'll say later what that exactly means. And ideally, we would just get the same theorems as the original Peterzil-Steinhorn theorem. However, currently in our preprint that exists right now, we have like a weaker statement. So we can only handle a case where G is sort of abelian. And the proof can work in a slightly more general setting, which I've defined here. So I'm going to say that G is nearly abelian if there is a definably compact definable subgroup K that contains the derived group, I guess. The point is just that K is a normal subgroup, G mod K is abelian. So there's like a compact group, the normal compact group that you could mod out by and get an abelian group. Okay, so if we have a group, if this group G, this definable group in a p-adically closed field, if that group is nearly abelian and if it's not definably compact, then we get a one-dimensional definable subgroup that is not definably compact. So this is supposed to be an analog of the original Peterzil-Steinhorn theorem. We think that we can prove this in the general case without this assumption that G is nearly abelian, but we need to do some additional work. And if there's time, we'll sketch how we plan to do that. So let's see. This doesn't say anything about this whole mu stabilizers picture, and it turns out that over the p-adics, the mu stabilizers are a bit not as well behaved. Like mu stabilizers will be type definable groups instead of definable groups. And so in order to really get a precise statement about mu stabilizers, we have to go to an Aleph-1 saturated model. And then if we have a definable one-dimensional type that's unbounded in the sense that it doesn't concentrate on a definably compact set, then you can show that the mu stabilizer is a one-dimensional type definable group. And that group is sort of, if the group, as long as the ambient group is nearly abelian, then we can show that this group is, I don't want to say it's not definably compact because it's not a definable group in the first place, but I'll just say that it's unbounded in the sense that it's not contained in a definably compact set. So yeah, right, the problem is, the reason why it's a bit messier than the original theorem is that this mu stabilizer is a countable intersection of definable groups. You have to take an intersection of, like, every formula in the base language, in the language of rings, gives you some different stabilizer, and then you have to take the intersection of those. In an O minimal setting, you have a descending chain condition on definable groups. So any intersection of definable groups is still definable. And this is really false over the p-adics. Like, it's easy to find like a descending chain of subgroups of the additive group or whatever. So that's why this thing becomes a little bit more messy in this setting. Before discussing like the main ideas of the proof, let me just say sort of where we hope to go from here. So first of all, we want to extend this to just, we want to get rid of this assumption of nearly abelian here. Yeah, then we would get like a better analog of the original Peterzil-Steinhorn theorem. We also might want, so Newman has the idea that like we have the theorem now for abelian groups. And so what we know is if you have a definable group that's not compact, it's got a one-dimensional definite subgroup that's not compact. Maybe if you're only looking at abelian groups, you can take the quotient, or you can sort of take the quotient. You might not exactly get a definable group, but at least the idea is maybe we can sort of use this to try to analyze abelian definable groups over the p-adics and get like a classification or just like a better understanding of what's going on with them than we currently have. Also, there's lots of different ways that we would hope to generalize this result. Like the original Peterzil-Steinhorn theorem isn't just for real closed fields, it's for O-minimal structures, which is a much bigger class. So here, the natural analog would be the p-minimal structures. And maybe maybe the same proof works for them, or maybe we can generalize to that case. We've also looked at or thought about generalizing it to groups that are definable in sort of dp minimal fields or dp minimal valued fields, because the p-adics are sort of a prototypical example of that. All right, so now I'm going to go on a little digression and discuss what exactly definable compactness means. So first, in the O-minimal setting, okay, let me say what I mean by a definable manifold first. A definable manifold is a definable topological space. It's got a finitely many, an atlas with finitely many open sets, and each of them is definably isomorphic, homeomorphic to an open set in M to the n. You could consider like maybe a slightly more general version where you have a like a definable family of charts or whatever, like an atlas with infinitely many charts. I don't know how how these two concepts are related, but for our purposes, this is what a definable manifold is. So okay, I guess yeah, Anand showed that every definable group in an O-minimal structure is a definable manifold in a canonical way. It kind of makes sense that like you sort of would generically have a manifold structure because it's O-minimal, and then because it's a group, you could sort of slide that around, cover it with finitely many pieces that will give you a manifold structure. And right, so the paper by Peterzil and Steinhorn introduced this notion for definable manifolds of what it means for a set to be definably compact. I'm stating it in a little, I'm unintentionally stating it in not full generality, but yeah, a definable manifold at least is definably compact if for every continuous function f from 0 to infinity to x, the limit exists. So it's this curve completion thing. This is like commonly used to define definable compactness in an O-minimal setting. So the point is any definable curve has a limit, like sort of this idea that one-sided limits always exist. And so you can show like this notion has a lot of good properties. Like if your base structure is an expansion of the real numbers, then this will agree with regular compactness. You can show that in general, it behaves a lot like regular compactness, even when it's not the same thing. You can show that a product of two definably compact sets is definably compact. You can show a continuous image of a definably compact set is definably compact. I didn't actually define what it, whatever. So it's sweeping some details under the rug. So, okay, now we want to generalize Peterzil-Steinhorn to like p-adics. We need a notion of definable compactness there. Okay, so first let's talk about the manifolds. So you can do the same kind of thing over the p-adics. An n-dimensional definable manifold is a definable topological space. It's got covered by finitely many open definable sets. Each of them is definably homeomorphic to an open set in M to the n. This is the exact same definition. Again, Pillay shows that every definable group is a definable manifold in a canonical way. Okay, so far so good. Okay, now when we try to define definable compactness, something is weird where in the literature we can only find this definition, which is that a definable manifold or whatever, maybe a definable set in a definable manifold. Anyway, a definable manifold X is definably compact if whenever U is a punctured neighborhood of 0 and F is a continuous definable function from U to X, then the limit exists at 0. Okay, So this isn't quite right. There's some real basic, fairly easy ways to fix it, but the sort of problem is that, okay, so this definition literally there would be no definably compact manifolds except for the singleton. The problem is just like, it doesn't work for the same reason that it doesn't work in the minimal setting. Like, because you could have a function where the one-sided limits don't agree. Like, if you could write out the same definition in an minimal thing, and you will have a problem if you have a function f where the limit as you approach 0 from below is different from the limit as you approach 0 from above. And you get the same problem in the p-adics because there's more than one type at 0. I mean, more than one infinitesimal type at 0. So of course, in the minimal setting, you fix this by considering like the one-sided limit instead of two-sided limits. The problem is in the p-adics, you sort of have infinitely many sides around 0. Like, I mean, there's infinitely many infinitesimal types there, so you can't. Oh yeah, somebody asked, why is this limited to manifolds? Because I was being sloppy while I was writing the slides. It should be more general than that. I mean, it should be like definable spaces or definable sets and definable manifolds or something. Right, so there's a problem with this definition. There's some fairly straightforward ways to fix it, but you at least cannot fix it the same way that you would fix, the same way that you would do it for the minimal structures.
Maybe, sorry, Will, maybe the question wasn't about spaces versus manifolds, but manifolds versus just definable sets.
Yeah, I'm saying like the right definition should be definable sets inside of definable manifolds, or definably compact if something is true. I accidentally only wrote it for definable manifolds, but really you could just, X should really be like a definable set inside of a definable manifold, right? Like, I think is that what you're saying?
I don't know, I'm trying to interpret the question from Moshe, what he had in mind.
I was thinking about definable spaces, but I just don't see why the manifold. I mean, you need to be able to say what a continuous function is, and that's it, right?
Yeah. It definitely works for definable spaces. I mean, that's the right setting. I just wrote the wrong thing on the slides. Okay, so well, maybe this was overkill, but in our paper, we used a different definition of definable compactness, which ends up agreeing with this other one once you fix this one. But so it turns out there's sort of an abstract way you can define definable compactness. It at least makes sense in any theory and often does something useful. So suppose you have a definable topological space in any structure. Okay, I think this definition is due to Fornaciero. I might be wrong about that, but I think he was the one who found this. So anyways, yeah, X is, we're going to say that a definable topological space is definably compact if basically whenever you have a definable family, a filtered intersection of a definable family of definable closed non-empty sets, then its intersection is non-empty. There's a lot. Let me say this. Suppose that you have a definable family of sets F, they're subsets of X. Suppose each of them is a non-empty closed subset of X. Suppose that this is a downward directed, it's like filtered. Whenever A and B are in F, then there's an element C in F that's contained in the intersection. Then the intersection of this family is non-empty. So you could sort of phrase this as a filtered intersection of a definable family of non-empty closed sets is non-empty. This may look weird, but I mean, normal in topology, one of the ways you can define compactness is that any filtered intersection of non-empty closed sets is non-empty. That's equivalent to the more usual ways of defining compactness. So this is like a definable version of this. Okay, so it has this definition turns out to have relatively good properties in general, or like it has a lot of the same properties that we're used to. But first I have an example for some reason. Okay, so if X is compact in the usual sense, then it's definably compact. If you're working in like the real numbers, then well, the open interval is not definably compact because you have a family of closed sets. They're closed in this space. They're like relatively closed. It's a chain, so it's directed, and the intersection of all these, they're all non-empty, but their intersection as A goes to one of these half open intervals, that intersection is empty. So it's a failure of definable compactness. On the other hand, you can show it like if you're in an NSOP theory, any set with the discrete topology is going to be definably compact because there are no, you can't have one of these filtered families. I mean, it can't be that interesting because there's no chains. Yeah, so like a filtered post set or whatever is going to have a minimum element. So I think this is true. I'm not actually 100% sure, but I think it's true that like if you take the formal power series over the complex numbers as a ring, this is with its usual topology, it's like definably compact in the language of rings. So kind of analogous to how the p-adic integers are definably compact in the usual topology. And the reason why like what's going on here is that the complex numbers, the residue field are in SOP, so they kind of count as being compact. Okay. Also, in the O-minimal setting, this abstract notion agrees with the classical notion using curve completion. I think this is, at least it's mentioned in a paper of these people. And you can show in any setting that this notion of definable compactness has good properties, like products of compact sets are compact, unions of compact sets are compact, image of a compact set is compact, and so on. Like compact sets are closed if you're Hausdorff, a closed subset of a compact space is compact, that kind of thing. And if you're in the, I don't know why I wrote that. It's not important, but yeah, in the p-adics, you can show that like this does something reasonable, like a subset of m to the n. A definable subset is definably compact if and only if it's closed and bounded. Like if you're over the actual p-adics, that means that a definable set is definably compact if and only if it's compact in the usual sense. Yeah, it turns out that this gives a reasonable notion for definable manifolds. So, oh, sorry, there's questions. What are these questions? How is 0 to infinity lives inside the manifold in the definition of definably compact? Oh yeah, the image. This is, I guess, over in an O-minimal setting, there's a function, a continuous function, a definable function from 0 to infinity to the manifold, like a curve that's parametrized by 0 to infinity. Okay, sorry, maybe that question was a while back. Yeah, so okay, it turns out there's a good sensible notion of definable compactness for definable manifolds over the p-adics. There's the version using these filtered families, this abstract definition. Oops, but you can also say this something like the curve completion thing. If you have a continuous definable function defined on a punctured neighborhood of 0, you don't get a limit, but you do get like a cluster point, basically. You can also think of it in terms of one-dimensional types, sort of specializing to individual values. So it's equivalent to saying that every definable type in X that's one-dimensional, every one of those types is infinitesimally close to a point of X. Okay. And maybe you can also do every type special. That doesn't make sense. So, in the chat, it says there's also HL, maybe Roshovsky was there. I don't know. Definition, every type special.
Every definable type.
Oh yeah, sorry, every definable type. Yeah, right, that makes sense. I was wondering about that just now. I think, yeah, this seems right. Every definable type specializes to a point also. Okay, well, so enough about definable compactness. Actually, I don't know if I have any time now. How long is this talk actually?
About 12 more minutes.
Oh, okay. All right, so let me try to sketch now how we adapt the proof to the Peterzil-Steinhorn theorem kind of thing to the p-adics. So we've got our model of the p-adically closed fields. We've got a definable group G, and it's got a manifold structure thanks to Anand Pillai. And we're going to assume it's not definably compact, and we're going to take a curve or whatever. Like we're going to take a type basically that doesn't specialize to a point. We're going to take like a one-dimensional type that doesn't specialize to a point. You can kind of get it by taking a curve that doesn't have a limit and taking a point at infinity in a sense. Okay, so anyway, we get this one-dimensional definable type P that doesn't specialize to a point. And we want to understand the mu stabilizer of P, because we're going to try to follow the same strategy as the original theorem. Okay, so several things are different over the p-adics. I mentioned this earlier that will sort of like in the o-minimal setting, 0 has sort of 2 sides to it. And I don't know if this is that important. Oh, but it does. Okay, so definable types, one-dimensional definable types in an o-minimal setting kind of have they're generated by like a definable family. Like you can sort of like they're like very definable. Like there's a filtered definable family whose intersection is the type or whatever. That doesn't really work for so it's like this family of formulas, if you're in an o-minimal setting, that like defines type. And this is a single nice definable family of formulas. You don't really get that over the p-adics. And this causes a few problems, but not that many. Yeah, like the sort of connection to 0 and infinity having infinitely many sides is that like these one-dimensional definable types are all like, okay, one-dimensional definable types in the home sort are all infinitesimally close to 0 or infinity or to some other point. And so sort of up to translation and stuff, you can kind of understand them by looking at types that are around 0, and there's infinitely many of those, like one for each coset of the connected component of the multiplicative group, sort of. A bigger problem is that there's no descending chain condition for definable groups. This interferes with some of the steps of the proof, and it makes this mu stabilizer thing be type definable rather than definable. It's not that type definable though, or it's a countable intersection of definable groups. So by making our models be like mildly saturated, it becomes not a big issue. Okay, the big problem is that curves are really not connected. I mean, over the p-adics or any valued field, everything is totally disconnected. That nice argument from earlier, where you have a curve and it has to go from the inside of the annulus to the outside, doesn't really make sense here because everything is definably totally disconnected. So that's sort of the difficulty we encountered and where we had to come up with a new method. So if you think through what it would look like for that, the thing you want to be true, like what it would, if it fails, like what the curve has to look like. The curve has to look like this kind of picture over here. Like in order for this the argument that the point of this annulus crossing argument from earlier was to show that the mu stabilizer is like not definably compact or something. And if the annulus crossing argument fails, it has to be because this curve, this like one-dimensional set C, it has to consist of infinitely many islands that are all of like a bounded size. And the sort of distance between the islands goes to infinity in the limit. So maybe so here's a picture of showing what that might look like. You have these different regions, they're all about the same size, but as you go to the end of the curve, the gaps between them get bigger and bigger. The sort of reason why this messes up the argument is if you picture moving a window along this like curve, as you go to infinity, that window, no matter if you have a fixed window with fixed size, it will always just see the little island they're in. It will, in the limit, like in the limit, it will look like there are no islands nearby. And no matter how big of a window you make, this intersection in the limit will be bounded in size. So in this talk, I'm calling this sort of distant islands configuration without making it very precise. There's going to be a lot of hand waving soon. So the idea is that if you have this kind of thing where there are these gaps that spread out a lot, this is going to contradict the fact that in the p-adics, dp rank is finite. So there's this notion, okay, dp rank is this notion of dimension that makes sense in any dependent theory or any NIP theory, and is especially good in certain theories like the p-adics where it's always finite. And so this sort of picture here, it's a little bit reminiscent of this structure here, where we take the real numbers as an ordered group and we tack on a predicate for the powers of 2. So it turns out that that structure is actually NIP, I guess by a theorem of Gunaydin and Hieronymy. And then, however, it doesn't have finite rank. It doesn't have finite dimension, as it were. And this is, you can see this using the fact that you have this sort of set where the gaps between things get really big in the limit. So let me first explain why having these big gaps, like why having large gaps leads to infinite dp rank. So first, let me sketch the idea. Here are some sets. X is 1, 2, 3, 4, 5. Y is 10, 20, 30, 40, 50. Z is 100, 200, 300, 400, 500. So there's an injective map from x times y times z to r that sends x, y, z to x plus y plus z. That's very clear. And if you think about why this works, it works because, well, it works because of powers of 10 and decimal expansions, but really the reason why it works is because all of the elements of y are really far apart. They're all like 10 multiples of, they're all 10 or 20 or whatever apart from each other. And 10 is big relative to these values. Was there a question? Okay, and then similarly, the elements of z are really far apart relative to the size of the elements in x and y. So suppose, I don't know, suppose we were in like an ordered abelian group and we had some definable sets, S1 through Sn. Suppose that like each of these sets is really far up, like the individual elements in it are really far apart relative to the previous sets. So for any x and Si, if y and y prime and Si plus 1, if y and y prime are distinct, like if they're not the same, then their distance between them is really big compared to x. Under this kind of assumption, this map defined in the same way will be injective, like the map from S1 cross S2 cross all the way up through Sn. Product of all those, it will have an injective map into R, sends x1 up through xn to the sum. And using the fact that the like gaps between things get spread out, you can see that this is an injection. And so sort of by properties of dp rank, because it's like a dimension, that if you, oh, sorry, these xi here should be si. Like if all these sets are infinite and definable, then they're going to have dimension at least 1. Their product will have dimension at least n, and R has to have dimension at least n. And so if you can make n arbitrarily big, then this structure has to have infinite dp rank. So in this particular structure that was looked at by Guniden and Hieronymy, here's how you could, one way to see that it has infinite dp rank. You go to a big monster model. You recursively build some sets S0, S1, S2, such that each of these is like an infinite, but bounded, like it's infinite from our point of view, but it's sort of finite from the point of view of the model. And it's like a non-standard finite thing. And it's a convex segment of the non-standard powers of 2. And you want to choose these things so far out that each like Si plus 1 is chosen so that any 2 elements of Si plus 1 are really far apart relative to all the sets that came before them. It's possible because powers of 2 get really far apart as you go out to infinity. So then you get the injective map for any n. And so the dp rank of the structure is at least n. N was arbitrary, so you get infinite dp rank. Oh, there's some technicality about dp rank being greater than Aleph 0 versus being greater than Aleph 0 minus. And so being a bit hand wavy, but it doesn't matter. The point is it's at least not finite dp rank. So something similar, without going into any details, something similar works in our case. We've got a definable group in the p-adics. It has finite dimension. Dimension is the same as dp rank in this setting. So the dp rank is finite. And you can show if you had this sort of distant islands configuration where you have this curve that you're trying to run the arguments on, if it has these individual islands that get really spaced out, it ends up behaving like the 2 to the n example. And you can show that the dp rank is infinite, which is a contradiction. And if that configuration doesn't occur, you can run the same annulus crossing argument as before and show that the group the mu stabilizer is not definably compact, whatever it was that we wanted. Unfortunately, like all my examples have been I've been writing them in abelian notation, and it's because once you actually try to make this argument precise, you really need G to be abelian, or at least kind of approximately abelian. The sort of source of the problem is that it depends, like you need to talk about things being far apart. There's 2 different ways. In order to talk about things being far apart, you need like a uniformity basically on this group, like a uniform structure. And a topological group is naturally a uniform space or whatever, but it's in 2 different ways. There's like a left uniformity and a right uniformity. And when you try to run this argument, you need to like sort of switch. You have to conflate those 2, the left uniformity and the right uniformity. It turns out that's necessary. I don't know. I tried very hard to find ways to get around this and it could not. So for now, this argument really only works if G is abelian or approximately abelian. I think that's am about out of time, so I won't really say much about the non-abelian case, but I will say that by mixing together a bunch of ingredients that I'm not going to read, we think that we can show the main theorem that if you have a definable group that's not definably compact, and we're in like a p-adically closed field, then there's a one-dimensional definable subgroup that's not definably compact. But at this point, we're just we're giving up on mu stabilizers. We're now just trying to, like, our strategy for proving this is sort of to kind of decompose G into simple groups and to abelian groups. I mean, not literally, because that wouldn't work, but that's sort of the spirit of the proof. And also, I haven't really written out the details of this yet, so this may not really be true, but we have a pretty clear idea of how to prove it. I think I will not go through that. I will probably post these slides so you can look through it on your own. There's a lot of asterisks here because every one of these statements is not actually true. But yeah, anyways, we throw together some representation theory and some other stuff, and things somehow work out. We also think we can generalize these kind of things, or I don't know, we might be able to generalize it to groups definable in other DP minimal fields. Well, okay, yeah. This definition won't mean anything unless you know what DP rank is, and then you probably know what DP minimal means. But yeah, there's a lot of other theories that have this property, like, well, real closed fields, algebraically closed fields, p-adically closed fields, ACVF. And we kind of, except for ACF, where there's no good topology, in any ways, it was considered by some other people, I forget who, kind of found analogs with Peterzil-Steinhorn in that case. In all these other cases, there's a topology floating around, and we think maybe we can get like a similar theorem in that case. There's sort of a minor problem that there's no Skolem functions anymore, no definable Skolem functions. I think it doesn't matter that much. The bigger problem is that maybe definable compactness doesn't work. Like with the definition from earlier, ACVF is not like locally compact or whatever. I have an example discussing this, but it sort of makes sense that like the open sets have, I don't know, if you think about it for a bit, you can see why it's true. So, well, this last slide is discussing like a possible alternative. If you kind of just change up the definition of definable compactness to only consider definable families of non-empty closed sets that are indexed by the value group, it seems like this gives a reasonable notion that does what we want. And my hope is that using this method, we can write down similar theorems for more general settings. Okay, that's it. I think I've gone a little bit over time. Anyways, yeah, are there any questions?